All right, welcome. We're going to do some asynchronous machine stuff today. We're actually going to see how we can get the asynchronous motor, and we're going to really run it just as a motor. We could actually run it as a generator, but very few people actually do run it as a generator, unless, again, you're working as a wind turbine company, and then you use the round rotor design to really optimize the power output. So we're going to go ahead and just run this as a motor. That's when the vast majority of these applications provide, and we'll do that. So I'm now got the basics of this lab set up. I've got the dynamometer kind of ready to go, powered up with the DAC power supply kind of being the consistent point or the node point. You can see I've got some green lights on here and here. I've also connected the torque and the speed output from the prime mover, and you also have to run the ground. I powered up the DAC in terms of the actual power requirements. I'm also going to switch this to the dynamometer to make sure I'm on dynamometer speed. And now I'm going to go ahead and start wiring this up. Now, this is up to you, but I'm going to simplify the wiring a lot because we've learned a lot in this class. So let's use some of that knowledge that we've gained. So I'm going to actually set this up to have as simple wiring as possible. I'm going to run my current to only one current source. And the reason why is because we've talked so extensively about a balanced system is as long as one phase is the same as the other two, we can get one phase results and then just multiply it by 3 and get exactly the same results that we need. So I'm going to connect this at a single phase for my power measurement. And then when I'm ready, I just want to go with a total input power is, I'm just going to multiply that value by 3, make it very simple. So I've got my one current. Now I've got to get my voltage. And so you can see I'm using phase A or phase 4, if you will. Let's just call it phase A as my power for the current. That also means I have to run the same voltage source to that as well. And that has to be a phase voltage. That's why I'm running it phase to neutral. And the reason why I do that is because when I look at my meter, you'll notice that if I, when I look at E1 and I1, but now I want to measure power on 1, you'll notice that it uses the current of the voltage on input 1 and the current on input 1 to measure the power. So I've got to make sure that I'm monitoring the phase voltage with the associated phase current, phase A, to get valid results. So that's the reason why I selected that. I'm going to turn these off because I'm not monitoring them. And then I'm also going to turn on my torque. Turn that on. And I'm going to turn on my speed and change this to corrected. Okay. So I've got speed, I've got torque, I've got those values. Now I've got to finish wiring this up. So because I'm only using a single phase, I can run these two phases directly in here because I don't need their voltages and currents. I'm going to estimate them based on what I'm getting from the single phase for phase A. And now I'm going to finish connecting this up as a Y. And there you have it. I now have my machine that is all ready to go to be able to do the measurements that I need for this particular lab. So I will pause for a moment and give you all a chance to see if you get the same results or the same configuration. So basically, I'm right at the point where I'm at step 5 because this knob right here is set at its minimum. So I'm ready to energize. Can we go ahead and energize, or do we need a few minutes here? Anybody need a few minutes, or?
I think I'm good.
Okay.
I'm all set as well.
All right.
Yeah, I'm all set too.
Let's flip the switch. Crank it up. And you can see that these are running in a clockwise direction. Okay. And with this particular dynamometer, it doesn't really matter. You can go in either direction. But at this point, you have enough data. You can do part number 5. What is the no load speed? 1775 RPM. Why is it no load? Because you can see that this is turned at its minimum. Now, you can't the true no load speed would be to completely remove this belt and not include it. but we only can measure torque with a dynamometer. So we need this belt over here to have some ability to measure torque. So for part 1 or for part 5, what's your speed? 1775 RPM. The next step is the no load speed almost equal to the full load speed? Well, this is a 4-pole squirrel cage induction machine. And if you remember, a 4-pole machine has a synchronous speed of 1800 RPM. So with that, I'd say, yeah, that's actually really close. I'm getting almost 1800 RPM. So the answer for part number 5 is a solid yes. All right, so now I'm going to turn on my continuous refresh. And remember, I've got to get to about 175 watts. This is only a single phase value. So this value multiplied by 3 is going to get me the results that I need. So if I take 175, divide that by 3, should be able to do this on the top of my head, but for some reason, I want to say 68, but I know that's too high. 58, there we go. So when this gets to be around 58 or so, I'm good to go. I'm going to move it onto a different screen and I'm going to slowly turn this up. And when I get to around 58, I will bring it up to screen. Really hard to get it close. So we're not going to build a piano. We'll just get close. All right. So at 61, which is a little bit more than 58, but that's close enough. Our speed now is 1744. So you're going to record your data. So we're getting an input power of almost 175 watt. Let's call it 181, close enough. Our speed now is 1744 RPM. And now our torque, which is in Newton meters, is 0.728 Newton meters. So that's what you're going to record. You're going to record your speed, your torque, and your current. Let me know if I can proceed. Can I proceed, or are we still working on this?
I got it.
Yeah, I'm just about done.
Yeah,
Okay.
I just got it too.
All right, so let's turn this back all the way to 0. And now I'm going to turn on this meter here, and I want this to be PQS1 because I actually want this to be reactive power, okay? So this is currently the single phase equivalent of the reactive power. So again, I just need to multiply this by 3 to get the actual power demanded. And so what I'm going to do is I'm going to set up my data table because I need to record the voltage, which this says it's a line voltage, but we'll call it a phase voltage. That's perfectly fine. The line and the phase current's the same, active and reactive power, output torque, and speed. So I basically am going to turn on E1, I1, here, here, and here. And here are my values. I've got E1. Oops, I forgot current. I apologize. Let me turn on current. Current over. Sometimes it allows you to do it. Sometimes it doesn't. It doesn't allow me to do it. All right. So here's your data. So now we're ready to go. We've got our value set to the minimum here. So we're going to go ahead and start doing a recording. So we're going to record our first data point. Now we're going to bump it up so that we've got to go up by 0.3 Newton meters. So I'm going to do this on the side because I don't have the screen. So actually I can share both screens. So let me pop this up and then I will share both screens. that over there. And I'll put this next to it. As long as I can see the torque, I'm okay. All right, so now I will share both screens. And hopefully you can see both my screens. Is that correct?
Yep, I can see both.
I can see him.
Okay. So now I'm going to adjust my dial. So this goes up to by 0.3. So right now it's 0.331. I'm going to increase it until I get to 0.6. So go very, very slowly. And what I'm going to do is I'm going to zoom way in to make the knob bigger, just to make it easier. So I just made the knob bigger. Close enough for me. So I hit record. Now I'm going to go up to 0.9 or around 0.9. Close enough for me. Continue on. 1.2. Jump there. Sorry about that. There we go. Here's 0.12, 1.2. And again, you don't have to be exact. You're just adjusting this as slowly as possible to get around the numbers you want. 1.5. Continue. Gonna go up to 1.8. You'll notice the speed is dropping. That's exactly what we expect, because when we did our torque versus speed characteristics, we had that discussion during class, we saw that as we get further and further away from synchronous speed, we get to higher values of torque until we reach a threshold, which we'll call our breakdown torque. And we'll go with that. So there's 2.4. 2.7. Pretty close enough. 3. Again, close enough. 3.3. Oh, what happened? Couldn't get to 3.3, could we? You saw that the motor slowed down. So we actually can't get to 3.3 because that exceeds the capacity of the motor. So now what we're going to do is we're going to go up and get pretty close to the 3. So we were able to get 3.05 or roughly. So let's see. That's probably the best I can do. And even then you can see it's kind of bouncing around a little bit. And it's slowing down. So this is too much. So I can't even get to 3.2. Let's try it again. Let's get it up to speed. And I'm going to try 3.15. If I can get there, great. If not, even here, it's slowing down. So I can't get there from here. I was able to get there. And what's happening is I'm unable to get to the actual peak because the way the curve is, curve up. I have it printed and I close it. Sorry about that. So the torque versus speed characteristic, what's happening is I'm getting to the point on the curve where I can't actually, I'm getting over here. So I'm not getting far enough up on the curve where I can get there. So I'm kind of missing that peak value. I'm close to it, but I'm not exactly. So when all is said and done, now we're going to go ahead and get a couple measurements down over here for this low value. So I'm going to go back and I'm going to kind of crank the motor all the way up and then let it stabilize. So this is not good for the life of the motor, but we'll do it very quickly. We'll do this a couple times. And if in the real world you were doing this, you could do something similar to this. What you would do is you would just take, adjust it. So now I've got it max over here. Now I'm going to back it off and let it have a chance to cool. So it's going to get up to speed and I'm giving it a chance to cool by running at full speed, because the way a motor works is you have fans, they cool themselves, makes sense. Now I'm going to go back all the way, crank it, and then I'm going to back off just a little bit. And then let's see if I can get a slightly different torque value. So the torque that I was putting out over here, 2.07. which you can see is kind of in the same area when we're over here. So on both sides of the curve. And now we see that we really didn't get any change. So let's see if I can turn this up a little bit. Still no change. No change. Okay, let's see if this one is okay. You can get a stable point here. But we need that. You can see that the speed and the torque are continuing to increase. So let's see if we can, if it stabilizes. It might be now that it's going to go all the way to the other equilibrium point. Yeah, you can see that we've lost it. So we can't get there from here. We can only get one low point. So your speed, your torque versus speed characteristic, this is what you're going to plot. So you're going to copy this and dump it into Excel. Or we'll use whatever application you're most comfortable with. And let's do a blank. I'm going to copy this data. Paste it over here. So this is my phase voltage. So this is V phase. This is my phase. This is my torque. This is my phase current. This is my speed. I'll put this in RPM just for clarity. Now, this is where I got to be careful because this is power, right? This is power and this is Q. And so these are single phase quantities. So I'll put P1 and Q1. I'm going to insert a column over here that I want PT, which is my total power, which is going to be equal to this cell multiplied by 3. So I've got to make sure I multiply that value by 3 to get the correct result. And you can see under this locked rotor condition, even though the torque isn't that much, it's putting out 1160 watts. And the reason why it's doing that is power is equal to torque times omega. The torque has gone down, but look at the speed. The speed is only 191 RPM. So pretty low. So now I'm going to do the same thing for QT. That's going to equal this cell multiplied by 3. And I have my Q values there. Okay. So we tried to get 0.1 changes, but we weren't even able to do that. So this is the best we can get. So now we're going to do a torque versus speed characteristic. Here's my torque. So I'm going to select this data point. Here's my speed. And I'm going to insert a plot. So it's an XY scatter, smooth. Now, does this look correct? Not correct, right? Because this is the torque and this is the speed. I want to swap those around. So you can change your data by selecting it. You hit edit, and then the sheet name, we're just going to type in torque versus speed. And our X values has to be the speed. And our Y values have to be the torque. And that looks like a torque versus speed characteristic. So from this data, you can pull out the breakdown torque. The breakdown torque is right at this peak value. So our breakdown torque is 3.05. Our locked rotor torque, what it pulls at locked rotor, is right over here, 2.07. So T, we'll call it BR for breakdown, is equal to the max value that we can get for torque, 3.047. And the locked rotor is going to be equal to the torque that actually is, if we could actually lock this rotor, and we can't do it, if we could lock the rotor in its position, then that's the value that we would get, 2.07. Both of these are in Newton meters. Okay. If we could actually lock this down, it would be a slightly lower value, but this is the best we could get. And again, this torque versus speed characteristic, you'd like it to be a little bit smoother up and down, but we can't get these points here. The equipment is just limited. The type of equipment that we have is just limiting in terms of what we can do. So we have breakdown and lock rotor torque. We also see that, let's see. So how does that compare to the nominal value of torque? Can anybody tell me what the nominal value of torque of this machine is? Move some wires around so we can see the main plate. Can you see anything? Well, look at this motor rating here. Motor is rated for 200 watts. So we can convert that to power or torque by just going back, and we'll do this in Excel. So we know that power equals torque times omega, right? And if we look at our power, or what our power is, we can see that we can try to calculate it, but we know that our nameplate, it said at about 200 watts is when it gets to its nameplate. So when we look over here in our total power, somewhere between these 2 points, that's where the nominal torque occurs. So it's going to be between 0.625 and 0.914. That's what our nominal torque is. So how would you calculate nominal torque? We don't have the exact value for 200 watts. So how would you calculate that? Anybody know the concept of linear interpolation? Or essentially the change in X over the change in Y. So we see that the dy that we have is equal to well, let's just type it in this way. It's equal to this one minus this one. And that's the difference. And then the dx is going to be equal to, same thing for torque. So it's this one minus this one. So now we have the change in y over change in x. So we'll just do that as a slope. So m is equal to this divided by this. So now we have the slope. And so all we need to do at this point is figure out how far we need to get to the 200 watts. So over here, we have to get 39 or 38.22 of an increase. So we need, let's see, how do we write that? So we need 38.22, I would say equals, multiplied by this slope. Now that's way too high. Why is it way too high? Anybody want to guess? That's the difference between the two. We have the slope, but all we've done is we've just multiplied it by the change in y. We also have to do the change in x. So then we have to multiply that by, let's see, this one minus this one. Oops, I hit the wrong button. Oh, sorry. Try it again. Oh, wait a minute. I think I'm doing this incorrectly. Bear with me. Let me check my calculation here. Trying to get that value. So for the near interpolation, we just need to get a ratio. I need to increase my torque by, or my power, I should say. I need to increase my power by 38.02. That's the power, the delta P that I need. Delta Y. No, the delta, the omega doesn't really matter. I really just need to change can also do. Well, I can make it even easier. I can assume it's linear. So to go from point, to go from 161.88 all the way to 221.85. The increase. They only need to go up by 38.12. So all I need to do is just divide that. So, okay. Sorry about that. I did more than I needed to do here. That's cool. So the first thing I'm going to do is get the delta P just between those 2 points. So this is linear interpolation. I'm taking the difference between here minus here. Now the actual, what I actually need to get to 200 is the actual. So this is what I'm going to increase above the 161.88. That's going to equal 200 minus here. Now I can ratio that. So this divided by this is the difference that I need to go between here. Now I've got to do the same thing for the speed. So this is the dp. Now I'm going to do the d omega, or the dn, I should say, for speed, since it's in radians per second or revolutions per minute. And I'm going to get the difference between the two. So it's equal to this. It's that. Let's build that. Equals that minus that. And so now I know that I went up. Whoop, so it's equal to this. So now I went down 24 RPM. So all I have to do is do the ratio of this. So the actual is going to be equal to this times my ratio. So my speed now, what I have to go, the difference between the two. So the speed, again, this is assuming linear interpolation, is going to be equal to the 1728 plus that value. So I'm calculating it's going to be around 1712.7 RPM. That's what it should be. Yeah, this is linear. Let's see how that compares to the nameplate. The nameplate says it's 1685. So it's in the ballpark. It's about 30 RPM off. So I can't be perfectly linear. You can see that I'm not in the linear region, but I can just use linear interpolation to do that. So how close is it? It's nominally close to doing it. So it's pretty reasonable. But more importantly, the torque, we said this is 3.05 and 2.07. The nominal torque, so T nominal, that's going to be equal to power equals torque times omega. So torque is equal to power divided by omega. So we divide the power, which is 200, and then we divide by omega, which it said from the nameplate, it's 1685 RPM. That's 1685 RPM, right? But that's not anywhere near what we have to do. And the reason being is the 1685 RPM has to be converted to radians per second. So 1685, we have to multiply that by pi and divide by 30 degrees. I'm going to call it pi like that. And that's the actual speed in RPM. So our nominal torque is not going to be the 1685. It's going to be that value. So 1.13 is the nominal torque output. How does that compare to block our breakdown? It's quite a bit less. And also, it's quite a bit less than our lock rotor, which is okay because we want these machines to operate fairly efficiently, which means that we have to have a pretty low slip. We want to be close to synchronous speed. So we know that the breakdown torque, which is the maximum torque this machine can do, is going to be much, much higher than the nominal torque, which is a good thing because if we have something that's kind of blocking it in position, it's hopefully able to break that free. But that also applies for starting conditions. So for starting torque values, we're getting quite a bit higher, almost double what we need. And that's what we said, if you remember from class, your locked rotor conditions are typically 200 to 300% of your nominal torque. Okay. Any questions on step 10? Because it says, or step 9, I should say. Let me know if I'm going too fast. Can slow down. Questions on that? I need feedback to see if I should continue or should I pause for longer and give you a chance. Like I said, because the eclipse today, I'm trying to expedite you all getting the lab so you have time to view it, but I want to make sure that you're also learning the material, learning information.
Do you mind showing the equations for dym act ratio dn and then the second act that you had? I kind of missed those as you're going kind of fast.
Yeah, so this is just linear interpolation. So essentially what I'm doing is, let me bring up whiteboard here. Sorry. It can be really difficult. So what's happening is, let's whiteboard start back up. You're just assuming linear interpolation to make it easy. So if you have a line, if you have a line and you have a point here, if you have 2 points and you're trying to get the difference, like you're trying to actually calculate something over here, there's a couple ways to do it, but essentially what you need to do is you need to get the delta, we'll call it y in this direction. And then what you need to go from this point to here, or actually, and then you have a delta x in this position. And then this point over here, you need to get, okay, to go from here to here, I needed this much speed. I'm now only going this much. So you can ratio it essentially as I've got to get, let's just say that this full length is 50. The delta x is equal to 50, but I only need 25 to go here. So the full 50 corresponds to a delta x, a delta y of, I don't know, 125. That corresponds to 125. If I only want to go up 25, then I ratio the 25 to 50, and then I multiply that by my 125, and then I add it to whatever point I have over here. So we'll call it our starting x. And that's how you use linear interpolation to get a point between these two. It's something you probably have seen many times. That's essentially what I was trying to show you to get over here for linear interpolation. We ultimately don't really need it. All we really need to do is to see what's my nominal torque and how does that compare to my block rotor and my lock rotor condition. So you really don't need that information to do that. So I probably gave you more than what you needed. I was trying to show a speed perspective to see how close we were to getting the full, the nominal speed. So I calculated if we try to get up 200 watts, we should have a speed of around 1712 is by calculating it. But what we actually saw was 1685. So this one was not super accurate, but now this is our calculation. We calculated 200 watts. And over here, we could compare that. We can compare these torque values, the equivalent of 200 watts in torque. And we can compare that to these two. That's really what we need there. So you don't need this. This is just like added to see, okay, do we get 1685? Yeah.
Thank you.
All right, shall we can proceed on?
I'm all set too.
I'm good.
All right, so now all we need to do is one more set of curves, and we need P and Q versus omega. So I'm going to select P, and I'm going to select omega, and I am going to insert an XY scatter. And now we got to double check, right, to make sure our X and our Y is correct. So we're going to select data, and we're going to edit it. And we're going to make sure our X values are correct. Our X values are up to 1800 RPM, so that looks good. Our Y values are here, so that's good. So this one is okay. So now I'm going to change the series name to real power. Okay, I actually don't want, let me edit that. Don't want the title of that. So, well, let's keep it over there and see if it's smart enough. Now I'm going to add Q, my reactive power. So I have to add a chart. And so this is going to be equal to reactive power. And now I'm going to add my X values. It's the same one, it's the same speed. And my Y values are Q total here. Now, if you want to make it really pretty, you can select over here and you can add a legend. Put it on the right-hand side. That's typically where I do it. You can also add a title if you'd like. Chart title. So E and Q versus speed. Now you can start to make some decisions about the type of curve. So our real power is the blue line. Our reactive power is the Q line. So does this confirm that an induction machine always consume reactive power? Well, the answer is a solid yes, right? Because we can see that Q is always a positive number. We also see that an asynchronous induction motor also always absorbs real power too, because there's no external prime mover. There's no mechanical system driving this thing to operate. So these are both have to be positive. But since this is an induction machine, we actually see as we get closer and closer to synchronous speed, it actually starts to draw more reactive power. And that tells you that even if this was to go to zero, this still needs reactive power. And the reason that needs reactive power is because all of the magnetic field on the rotor circuit is induced from the stator set of windings. And the inducement is done by an equivalent inductor that those stator windings provide. So Eli the ice applies here because in an inductive circuit, the current lags the voltage, which when you do your power triangle, Q is going to be positive. So the answer is absolutely, it does confirm this. And it also sees that as we draw more load, right, we start to get more torque output. Our real power is greater than our reactive power. It always stays above there, again, except for really lightly loaded conditions. Okay. Questions on that? All right. Any further questions before we do the last part of 10?
Good.
Now, what's that?
I'm good. I think I've got everything.
Okay. So now all we need is do a graph that shows motor current as a function of motor speed. So again, we just do, whoops. We have to just do one more curve. So I'm going to calculate, I'm going to add speed. And I'm also going to include current. And I'm going to insert an XY scatter. All right, so this is backwards, right? I want the speed. So I'm going to go ahead and select the data. And I'm going to edit it and switch that around. So I want my X values to be speed. And my Y values to be current. And this is now going to be current. Okay. So you can name the axes as squirrel cage, induction, motor speed. That's pretty easy to do in Excel. You just add a chart. Whoops. You add a chart element here, and you just add an axis title. So we'll call it primary vertical. This is current. I can spell current correctly. And then we will add a horizontal axis, and this is speed. Oh. I don't. It seemed to not well, maybe I was a little fast, so this is current. So that's how easy it is. You can do stuff with Excel. You can add them pretty easy. So now the question is, how does a line current vary as the speed, as the motor speed decreases? Well, you can see that it goes up. And why is it going up? Because it's not providing as much torque necessarily, but it does need a lot of power to be able to drive that amount of torque. I need a lot of power to be able to do that. And if you remember the discussion when we talked about hydroelectric facilities, they run at typically very low speeds. So they need lots and lots of power output to be able to either drive the torque that's equivalent to the mechanical torque. So that would be the induced torque, or to be able to maintain a constant speed. So you need massive amounts of currents, 4 amps here, to be able to go at locked rotor conditions, where if you look over here, when I put out essentially the same amount of torque at 1584 RPM, I'm only needing 1.61 amps. So I'm putting out more than twice under locked rotor conditions, even though the torque. So another reason why I, as quickly as possible, want to get to here. I want to get to these higher speeds because I'm putting out just as much torque, but my current is going way down. So my motor is more efficient. Again, going back to our discussion about we want to maximize efficiency of our machines. So we want to run these as a higher level of slip as possible. Okay, so the nominal line current, go to the nominal line current. I'm going to bring up our plot here, and I'm just going to go ahead and stop this motor because it doesn't need to be running anymore. I'm just wasting quote unquote energy. And if you look over here, the nominal current is 1.14 amps. So the question was, where is the So the nominal current over here is 1.14, so just about over here. So you can see 1.14 or 1.15 as compared to 4. So that's over 3 times the amount of current that is necessary. So you're getting a value of 3 times that value, and you're putting out less. Okay. So the value is whatever, so the ratio, so that's let's put that as locked rotor nominal current. That's going to be equal to 4.028 divided by 1.15. So it's 3.5 times greater, which is actually a small amount. More often than not, it is 6 to 7 times. This is only 3.5 times that value. Okay, questions on that? All right, last part of the lab. We'll stop the motor. And all we're going to do now is we're going to swap any two leads. So I'm going to delete leads 2 and 3. Because right now, 2 was going to 5 and 3 was going to 6. And if I swap those and flip my switch, watch the direction. It was going clockwise, now it's going counterclockwise. So this is when we talked about when we were looking at magnetic fields and how we determined them with a 3-phase set of windings. We were actually able to get, we're actually able to change the rotation of a machine or the magnetic fields just by swapping any 2 phases. And you can see that we validated that here. We swap those 2 leads, it's going clockwise. If we swap them back, 6 to 3 and 5 to 2, and hit the switch. Now it's going clockwise. A second to update. So yes, it goes and swaps around. And that's it for the lab. Any questions? I know we went a little fast, but hopefully it's not too painful of a lab. It really is just doing a lot of plots in Excel. But we also did the discussion about, getting 3-phase quantities from single-phase values. So hopefully that was helpful as well. So questions? All right. Well,
I think we're good.
I'm all set, yeah.
all right. Well, I'll pause the video and anybody who has questions can stay on and stick around until they get the lab where they're done. If not, go enjoy the eclipse and I'll see you all tomorrow. So I'm going to stop the recording and stick around.